Assalamu alaikum class. In this video we are going to solve some questions related to chapter number 1. So here we have question number 10. Given two non-collinear vectors a and b, find an expression for any vector r lying in the plane determined by a and b. So at first we will discuss that what is meant by collinear vectors. So any two vectors that are parallel to the same line are named as collinear vectors. For example, this is my line and this is the vector a and here is the vector b. So then you can see that clearly a and b are parallel to the same line. So these are collinear vectors. Or on the other side, if this is my vector a and here is the vector c, then again the two vectors are parallel to the same line, so these are the collinear vectors. So in simple words, whenever the two vectors are parallel to the same line or the two vectors that are parallel or anti-parallel are named as collinear vectors. Now come to the non-collinear vectors. So non-collinear vectors means the two vectors that are not parallel to the same line. So whenever the two vectors are not non-collinear, they intersect at some point or making some angle with each other, because we know that the parallel vectors cannot intersect at any point. Similarly, the anti-parallel vectors also cannot intersect at any point. So whenever we are having non-collinear vectors, they can intersect at any point, making some angle with each other. So whenever the two non-collinear vectors intersect, they always construct a plane over here. So for example, we know that the unit vector I and the unit vector j both are non-collinear vectors because they cannot be parallel or anti-parallel to each other. So here is the unit vector I and here is the unit vector j, and we know that they intersect at an angle 90 degree and always construct a plane which is also named as the xy plane. Similarly, when the two vectors a and b intersect at an angle not necessary to be 90 degree, so they always construct a plane. So here we can see the plane over here. Now for the question, we have to find out an equation for the vector r which is lying in the plane. So let's suppose the point r is any point in this plane, and here is the position vector for this point which is unit vector, which is the vector r, and we want to construct an expression for this r in terms of a and b. So if I'm going to draw the corresponding component vectors, so here is OC will be the corresponding component vector and OD will be the component vector for the position vector r. So if OC and OB are parallel, it means they must be the scalar multiple of each other. So OC will be equal to y into b, where y is a scalar, and OD will be equal to x into a, where x is again a scalar. So by figure, OD plus OC is equal to the vector r. So XA plus YB is equal to the vector r. Obviously, the scalars x and y may be positive or negative depending on the situation or the orientation of the vector, and x and y are always unique for given vectors a, b and r. Or more precisely, we can define it in the terms that if x is the x component of the vector r and y is the second is the y component. If we are talking about the rectangular coordinate system, then we can write it as xi cap plus yj cap is equal to the position vector r. But if you are talking about any general forms a and b, then we must able to find out some scalars x and y that are going to satisfy the equation in this case. Next we have question number 12. Prove that a and b are non-collinear, then xa plus yb is equal to 0 implies x is equal to y is equal to 0. Here you can see that 0 is also bold over here. Bold means it is representing a vector quantity. So if you want to write it in your own, that is xa cap plus yb cap is equal to 0 vector. So you have to put the sign of vector over here, otherwise it will be a false statement, because addition of two vectors cannot be a scalar, so it must be a vector representation over here. So now we are given with that a and b are non-collinear, and we have to show that x and y must be equal to 0 in this case. So we will try to suppose it solve it on contradiction, or we are just going to suppose that x is not equal to 0. So we are taking a contrary example or the contrary supposition that x is not equal to 0. If x is not equal to 0, it means it can be in the denominator, it can be divided. So in this equation we can write that xa is equal to minus y times of b, or the vector a is equal to negative times of y over x into b. So it means that because x is not equal to 0, that's why this is a valid statement, otherwise it will not be a valid statement. Now you can see that a and b are scalar multiples of each other. If the two vectors are scalar multiple of each other, then they must be collinear, but it is a contradiction to our supposition, because we are saying that a and b are non-collinear. So it means that our supposition is wrong and x cannot be equal to 0. It must be equal to 0. So this supposition is wrong and we have to take x to be 0. Now if x is equal to 0, we can put this value over here. We get yb is equal to 0, and since b is a non-zero vector, so y must be equal to 0 in this case. So this is what we have to prove in this question. Next we have question number 13. If x1 a vector plus y1 b vector is equal to x2 a vector plus y2 b vector, where a and b are non-collinear, then x1 must be equal to x2 and y1 must be equal to y2. So here you can see that we can write it in the form, or we can shift this vector on the other side and we will get this equation, and then we can separate a and b, that is x1 minus x2 into vector a plus y1 minus y2 into vector b is equal to the 0 vector. As we have solved it earlier, that if we are having non-collinear vectors and their scalar multiple addition is equal to 0 vector, then the corresponding scalars must be 0. It means this scalar must be 0 and this scalar must be 0. So it means x1 is equal to x2 and y1 is equal to y2 over here. Next we have question number 19. Find an equation for a straight line which passes through the two given points a and b having position vectors a and b with respect to origin. So we are going to find out the equation of a straight line in terms of the vectors a and b, that are basically the position vectors of the points a and b. So let's suppose this is my point a and this is my point b, and a line is passing through these 2 points, and we are given with that the position vector, that is the vector from origin to the point a, is represented with vector a, and here we are representing the position vector of point b with the vector b. And let's suppose p is any point on this line and r is representing its position vector with respect to the origin. Now it is clear from the figure by head to tail rule that oa plus ap is equal to OR. So we are just adding the two vectors in order to get the resultant. So OA plus AP must be equal to R. OA is equal to A, AP as it is, and R is as it is. So we can find out the value of AP, which is equal to the vector R minus vector A. Now if I consider that again, that OA plus AB is equal to OB. So this is what we can see, that OA plus AB is equal to OB. So inserting the value, that is OA is equal to A, OB is equal to B, we get AB is equal to the vector B minus vector A. Now AP and AB both are parallel to the same line, or both are parallel, or both are collinear. So these must be equal to the scalar multiple of each other. So what I'm going to write, I'm going to write AP as a scalar multiple of the vector AB. M is any scalar over here. So inserting the value of AP and AB, we get the corresponding equation for the required vector, or the equation for the straight line. Next we have question number 20. Find the position vectors r1 and r2 for the points p and q respectively. So as we have discussed earlier, that we are just if we are having a point p with coordinates 2, 4 and 3, so we are, for the corresponding vector, we are just going to multiply the x component with the I cap, y component with j cap, and the z component with the k cap. So here you can see that the corresponding position vector is going to be 2i plus 4j plus 3k, and the corresponding unit vector for point q, that is r2, is going to be 1, that is I cap minus 5j cap plus 2k cap. So next part, in the next part we have to determine the resultant of these position vectors. So we have already discussed it about it. Whenever we have to add the two vectors, we are just going to add their corresponding components. As you can see that I vector can be added in y vector, j can be added in j, and then k will be added in k. So here is the corresponding figure as well, that here is my position vector r2, here is my position vector r1, and if I am going to add the two, so I have to place this r2 over here, and then I will add these two components. So mathematically it's quite simple, that just add the corresponding components in order to get the corresponding components of the resultant vector. Next, we have question number 24. Find a unit vector parallel to the resultant of the vectors r1 and r2. So at first we will add the two vectors r1 and r2, and for this we have to add x components, y and z components respectively. So here is the position vector for the point r, or the resultant of the vectors. Now we will find out the magnitude. That is, we are just simply going to take square root of the sum of the squares of the components. So 3 square plus 6 square plus minus 2 whole square root, which is 7. As we have discussed that for unit vectors we have to divide the vector by its magnitude, so I'm just going to divide the vector with the magnitude, which is 7. So here is a corresponding unit vector, and here is a cross check as well, that if I'm going to take the magnitude of this quantity, it must be equal to 1. Here is the next question, question number 25, in which we have to determine the vector having initial point P and the terminal point Q and find the magnitude. So let's suppose the initial point P is represented with x1, y1 and z1, and its position vector is r1 from origin, and here is a point Q with position vector r2, and we have to determine a vector with initial point P and the terminal point Q. So here is my corresponding vector. So by head to tail rule we can see that OP plus PQ is equal to OQ, that is R1 plus PQ, the vector, is equal to R2. So PQ is equal to R2 minus R1, and in order to solve this we simply subtract the corresponding x, y and z components. So here is the corresponding position vector. So whenever we are given with the points, the initial point and the terminal point of any vector, we can find out a position vector corresponding to it. And how we can find out PQ, and how we can find out, we have to subtract the initial point from the terminal point. Like you can see x2 minus x1, y2 minus y1, z2 minus y1. So we have to subtract initial point from the terminal point, and then we will get the corresponding position vector. Next we have question number 27. Determine the angles alpha, beta and gamma which the vector v makes with the positive direction of the coordinate axis, and show that cos square alpha plus cos square beta is equal to cos square gamma is equal to 1. So basically we are given with the vector v with the x, y and z corresponding components. So let's suppose this is my vector v. Here is my vector v, and it is making alpha with x-axis, beta with y-axis and gamma with z-axis. Again the vector is in space, not in any plane. So let's suppose the corresponding point or the terminal point is having the coordinates x, y and z, that is x component is x, y component is y and z component is z. Now consider, you can see that we are having three triangles, and we will consider the triangles one. Now here for the corresponding projection triangle on y-axis, we get cos of beta is equal to y over unit vector, the magnitude of the vector r, and for the triangle with z-axis, the angle gamma, cos gamma will be equal to base over hypotenuse, that is z over magnitude of the vector r, and for the corresponding triangle making on x-axis, cos alpha is equal to x over, that is base over hypotenuse, so x over magnitude of the given vector. So now I can simply add the vectors cos square alpha plus cos square beta plus cos square gamma, which is equal to 1, because the magnitude will be equal to x square plus y square plus z square whole square, and these two terms will be cancelled out. And here the cos alpha, cos beta and cos gamma are also named as the direction cosines of the corresponding vector.